In the last video, we saw that the two chair shapes, or the two chair configurations of just plain vanilla cyclohexane were equally stable. There was nothing that would imply that this is more stable than that, or vice versa. But what we want to do in this video is address what happens if instead of just a pure cyclohexane, what if we added a methyl group to it? And so instead of just a cyclohexane, let's think about a methyl cyclohexane. And so we know what to do when we're naming things. So a methyl cyclohexane will look like that. We'll have a hexagon here. This is the way we've been drawing it historically. We've been drawing it just like that. And then it'll have a methyl group. And you could literally just draw a methyl group like this, or maybe like this. And by implication, you have a carbon here, essentially a CH3 group here, and of course you have another hydrogen bonded here. Now, if you were to draw this methyl group in kind of 3 dimensions like this, it would look just like our different chair positions before, but instead of this H being just an H, we could make this entire methyl group. So we could turn this CH3 right here, so this, let me draw it out in a different color. We could make this carbon that implicitly has 3 hydrogens on it. So this is a CH3 group. That is a methyl group that's right there. We could turn one of these, we could substitute one of these hydrogens with it, and then this would be one of the shapes of this methyl cyclohexane. So CH3. Let me write it down just to practice our naming. So this is methyl cyclohexane. Now, in this is one of their chair positions. And then if this were to flip down and the other side were to flip up, the other chair position would take this methyl group from being in an axial position, and it would put it in an equatorial position. So this is the same group right here. Let me put a circle around it. It's a whole group. That's the CH3. Now, the question we want to answer in this video is, one of these two configurations going to be more stable? Now, you might just be able to eyeball it looking at this diagram and say, hey, when we're in the position where the methyl group is in the axial position, it's going to be closer to all of these other carbons over here, closer to their electron clouds. Maybe it has higher potential energy. Maybe it'll want to spring away. And if that was what you're guessing, or what you're kind of eyeballing, you'd be right. Because in this position, this methyl is much further away from all of the stuff out here. So there'll be less, I guess you can consider it, electron cloud crowding, if you will. Now, to see that a little bit more clear, I want to do what we could call it a double Newman diagram. And really, that's the whole motivation of this video, to kind of expose you to that a Newman diagram isn't just useful for simple things like a butane or an ethane. You can actually do it with cyclical rings. And to do the Newman diagram, let me number these carbons. So we could number them like this. So this is carbon 1, 2, 3, 4, 5, 6. And you don't have to call this one methyl cyclohexene, because whenever you have only one group attached to the ring, you implicitly start the numbering at the carbon that the group is attached. So that is the one carbon over here. This is the one carbon, 2, 3, 4, 5, 6. And over here, once again, this is the one carbon, 2, 3, 4, 5, 6. Now, what I want to do is draw two Newman projections, and both of them will involve, well, actually, I'll draw 4, but you'll see what I'm talking about in a second. So the first Newman projection, I'm going to start at this carbon that carbon right over there. So let's think about what that would look like. So we're at the front. We're staring straight onto that carbon. So this carbon's in the front. This carbon over here, this carbon number 2, is in the back. So let me label this. This is carbon number 1 that we're looking head on. Now, right in the axial position, you have that methyl group. So let me draw that. So in the axial position, you have that methyl group right over there. And then in the equatorial position right here, you have this hydrogen. So let me draw that. So you have this hydrogen. And then over here, this bond right over here, this gets us to another CH2 group. So let me draw that like this. So that gets us to another CH2. That's a CH2 right there, right? Or maybe I should circle it like this. This whole thing is a CH2. So it's bonded to the carbon, but the carbon has 2 hydrogens on it. And this is actually carbon number 6. So this is the front. Now, if we're staring straight and carbon number 2 is right behind it, let me draw carbon number 2. I'll do it in this blue color. So carbon number 2 is that bigger circle. Now, carbon number 2, what's going on over there? It has a hydrogen in the axial position going straight down. it has a hydrogen in the axial position going straight down. This hydrogen right over there. And then it has another hydrogen going equatorial. So this green hydrogen right here is going equatorial. It looks like that. And then it connects to carbon number 3, which is another CH2. It has two hydrogens branching off of it. So this right here, so this in front we have carbon number 1, in the back we have carbon number 2. Let me color code it a little better. Carbon number 2. And then carbon number 2 branches off to, so if you think of this branch right here, if you think of that branch right here, that's carbon number 2 branching off to carbon number 3, or CH3 right there. Let me do that in a new color. So this is or actually a CH2 group. That's a CH2. This is a carbon. It has two hydrogens, right? So this is a CH2. This is carbon number 3, right? This is carbon number 3 right there. And then that goes, and actually I'll pause there. What I'll do now is I'll draw another Newman projection. But for this Newman projection, we'll be looking straight on our carbon number 5. Our carbon number 5 right here. And we're going to form a ring, because the first Newman projection we just did essentially covers this bond. This bond is sitting straight into the screen the way I did it right now. Carbon number 2 is directly behind carbon number 1. So I guess the opposite side of the ring is 5 to 4. If you look at here, 1 to 2 is there, and then 5 to 4 is just like that. So you can imagine when we're doing the Newman projections, we're looking straight on here on the left Newman projection. We're going to look straight in that direction on the right Newman projection. So if we have carbon number 5 in front, what are its bonds going to look like? Well, it's going to bond to carbon number 6 right over here. So we can make this right. Let me do that in a different color. This right here, this bond right here, is this bond right here to that same CH2 that our first Newman projection bonded to. And then he's going to have two hydrogens. I haven't drawn them here. Let me draw them just so you can see them. Going to have two hydrogens, one in an axial position and one in an equatorial position. It's hard to see now, but he's going to have one hydrogen in axial and one in equatorial position. And then in the back, we're going to draw carbon number 4. And carbon number 4 I will do in this green color. So carbon number 4, or actually, well, yeah, I'll do carbon number 4 in that green color. And this is really just an exercise in visualization. That's why I wanted to do it with you. So carbon number 4 has an axial hydrogen. So it has a hydrogen pointing straight down. That hydrogen is that hydrogen. It has an equatorial hydrogen going out like that. And then it bonds to carbon number 3. So this bond right here is this bond, just like that. So what do we see immediately when we draw this chair position? When our methyl group is in the axial position, what do we see? Methyl in axial position. We see that it's gauche, or gauche, I don't know the best way to pronounce it. It's only 60 degrees away from carbon number 3. This is only 60 degrees, or our dihedral angle. You know, when you use the Newman projection, this is only a 60-degree angle. It's 60-degree angle. It is gauche to carbon number 3. It is gauche to carbon number 3. So maybe they're crowding each other a little bit. Let's compare it to the situation where our methyl group is equatorial, where the carbon that it's attached to is on the down part of the chair. Let's see what that Newman projection looks like. So same thing. Let me scroll over to the right a little bit. So this is this configuration, and it's in equilibrium. It's in equilibrium with this configuration right here. We'll do the exact same exercise. Carbon number 1, but now carbon number 1. In carbon number 1 right here, the hydrogen is now axial, and it's pointing straight down. So let me draw that. So we have a hydrogen pointing straight down now. Hydrogen's pointing now down, and now the CH3 is in a equatorial position, which you can see more clearly on this than over here. So you have a CH3. The methyl group is right there. And now this bond to carbon number 6 will look like this. So will look like this. So you have a CH2. This is number 6 right over there. And now if we were to go to back, if we were to go to carbon number 2 in back, which we had done in the blue color before, so I'll do it in the blue color again. carbon number 2 in black. It has a hydrogen in the axial position going straight up. That's that hydrogen right there. Has a hydrogen going straight up. Has another hydrogen over here. And then it bonds to carbon number 3 in the back. So CH3 or CH2 over here. So this guy's the same thing as this guy, but now we've flipped configurations. So he bonds to that guy in the back. And now we do the Newman diagram looking straight on to carbon number 5. Or looking actually straight on to, right, carbon number 5. So we're going to look straight in. So we're looking straight in this direction for this Newman projection. And now we're going to look straight in this direction for our other Newman projection. So carbon number 5. Carbon number 5, if we draw it in the front, it actually, I haven't drawn it here, but it has a hydrogen in the axial position, and then it has a hydrogen in the equatorial position. So carbon number 5, if we look at this, and this is really, if you're getting a little stressed out about this because it's a little hard to understand, you might want to rewatch it. This is really just an example of visualization. So I really hope this isn't confusing you. If you find this really daunting, this isn't going to really trip you up in the rest of organic chemistry. But if you can get it, it's even better. You'll be that much better at visualizing some of these molecules. So if we look straight on carbon number 5, we have a hydrogen in the axial position coming straight down. Hydrogen in the axial position coming straight down. It is bonded. Carbon number 5 is bonded to carbon number 6, which is right over there. So let me make it very clear. So this bond right here. Now I want to do a different color. This bond right here is the same thing as this one. This is a really good way to, if you can do this, then your brain is pretty good at translating between Newman projections and these kind of seat diagrams that we have up here. So this is this bond. This axial hydrogen is this axial hydrogen. And then we have another hydrogen. We have this hydrogen right here, which would be that like that. And then in behind it, you have carbon number 4. Carbon number 4 is, let's say it's like that. So carbon number 4, draw a circle. It has a hydrogen in its axial position, another hydrogen like that. And then it bonds to carbon number 3. So this was number 3 right here. So just like that. So what do we see about this methyl group here? In this situation, this methyl group is there's two ways to think about it. Its dihedral angle versus carbon number 3 is now 180 degrees. Over here, it was gauche. It was 60 degrees. It was dihedral angle to carbon number 3 was 60 degrees. Now it's 180 degrees. So it's much further. And now its dihedral angle to carbon number 6 is also 120 degrees. So in this situation, where our methyl group is equatorial. It's axial here, it's equatorial here when we jumped back down. Because notice, it's parallel, the bond is parallel to parts of the ring. In this situation, we are farther away from the other methyl groups. There's less crowding. And so this is a more stable situation. So you could say it is an anti-configuration. Configuration relative to carbon number 3, while over here it was gauche to carbon number 3. I don't know if I'm saying it's gauche. I don't know the best way to pronounce it. So in this case, there's less crowding. This is more stable, lower potential energy. More stable. So hope you found that interesting. This was really a way, just an exercise in being able to go from this visualization to kind of this double Newman diagram. And if it makes it any easier, the way you could think about it is we're viewing in this Newman diagram right here, where this carbon number 6 is this carbon number 6, this CH2 is this one back there. So when we're looking at it from this, we're kind of looking at this hexane ring from this direction. We see this in front. This is this, and we see that in back. That is that. Over here, same thing. We're looking at it directly. We're looking at it directly from this direction. We see this guy on top is over here, and this guy on the bottom is over here. So